Today I'd like to look at several applications of vectors. Really quite a fun topic and extremely applicable to the real world, very much so, in trigonometry. So we have a small tree here, and these ropes are supposed to be parallel to the ground, but because I'm in two dimensions I can't really show that. So would you pretend that there's a person over here? So here's a person pulling at 23 pounds of force, and here's another person over here pulling at 18.5 pounds of force, and they are perpendicular to one another, so this is a right angle, but I'm trying to show you this in perspective. So again, that's a right angle. What's the resultant force on the tree? So this is kind of getting you ready for harder problems dealing with vectors. And the reason this one's getting you ready is because they're perpendicular. So they're at a right angle. Their tails are together, and I just like to remind you of the fact that via a parallelogram, this is supposed to be a dotted line parallel to the 23 pounds, and this is supposed to be a dotted line parallel to the 18.5 pounds, that the resultant here is going to be found by going from where their tails are together to the opposite corner of the parallelogram. So here's my resultant vector. But remember, what you have here is a right triangle. So the 23 pounds is right here, while the 18 is right here. So I'm going to go ahead and just erase this just so you can see this. Let's see, get my eraser. So I'm going to put the 23 right here and the 18.5 right here. And so I have a right angle right here. And so I'm going to use the Pythagorean Theorem to find the length of that red line. So I'm going to take the 18.5 squared and the 23 squared, add them together, take the square root, or use your program, and find out that the length of that red line is 29.5 pounds of force because of these two people pulling at right angles to one another. I do need to find the size of this angle theta, so to do that I'm going to take the inverse tangent of the side opposite, the 23, over the side adjacent. Because this side is bigger than this side, I'm expecting an angle bigger than 45 degrees. You would get 51.2 degrees when you do that. And then finally, I would say that my answer to this problem is 29.5 pounds at an angle of 51.2 degrees with respect to the 18.5 pound force. Now, you know, you could find out what the size of this angle is too, and if that other one's 51, then this angle right here is 90 minus 51, so, you know, whatever, 38.8, I believe, and you could say 38.8 with respect to the 23 pound pull. Either way. So a simple one because they're perpendicular. And that's true for this one too. So a rocket is launched with a vertical component of 2,840 kilometers per hour and a horizontal of 1,520. So I'm going to try this vertical component to make it longer than this horizontal component of 1,520. And let's go ahead and label those. So notice I'm putting the tails together. I'm not going to put the units on for right now if you don't mind. So here's the 1520, and I want to know the resultant velocity. So remember, by a parallelogram, or, you know, I could have put the tail, this 2840 over here, of course, but by that parallelogram, the resultant is from where their tails are together to the opposite corner. I wish this was snapping right here where I want it to snap. And then, again, by the Pythagorean Theorem, I'll take the 1520 squared plus the 2840 squared and take the square root. And when you do that, you should get 3,221.2. Now the units for this are kilometers per hour. It's the speed of the rocket. So it's actually traveling this way with a horizontal component of the 1520 and a vertical component of the 2840. I still need to find this angle theta. So theta is found by taking the inverse tangent. So please notice a lot of Pythagorean Theorem and a lot of tangent. So the side opposite that angle is the 2840, and the side adjacent is the 1520, and when you do that you get 61.8 degrees. So when I report this answer, I'll say that the resultant is 3221.2 kilometers per hour at an angle of 61.8 degrees, but I have to say from the horizontal. I have to say with respect to what? And so this 61.8 degrees is with respect to this horizontal. All right, let's see. The next one's pretty interesting. I'm going to be breaking my videos up in terms of applications. And you know, in all honesty, I'm going to skip this one for a minute and make this segment a little bit easier, video segment. And so I'm going to skip to number 4 next, and I'll come back to number 3 in my next unit. So in number 4, again, two perpendicular forces act on a ring at the end of a chain. So here's my ring at the end of a chain that passes over a pulley and holds an automobile engine. If the forces have the values shown in the figure, what is the weight of the engine? So I have to tell you, the one thing that's not stated in this problem is that this needs to be a frictionless pulley. So let's go ahead and say that. It's got to be a frictionless pulley for me to be able to acknowledge or say that the resultant force of this vector and this vector, which is, that resultant force is this red line, and I didn't make it a straight line, I'm sorry. I might actually fix that. I can't stand it when I don't do that. So here's my straight line. Well, I'm just going to go ahead and draw it again because it doesn't want to snap. So there's my resultant. For the weight of the engine to be equal to this red line, so what's going on here is that there's the tension in the cable is equal and opposite to the forces acting on the ring. In order for this thing to be held, the automobile engine is held. It's not moving anywhere. So whatever this force is, the tension in the cable has to be the same in order for this to hold still, to be static. So, you know, first of all, I'm just going to go ahead and use the Pythagorean Theorem. So 490 squared plus 120 squared, and then take the square root. And when I do that, I get a value of 504.5, and the units here are pounds for this. You know, that's my answer. That's all I need. How much does the engine weigh? So here's the deal. If the tension in this cable has to be equal to this resultant in order for it to be held, it passes right on over to the engine. So the engine is pulling with 504.5 pounds of load, and therefore this cable has that kind of tension in it of 504.5 pounds. These two are equal to one another and opposite. Frictionless pulley is the only reason that works. And then we got to have the people over here holding that 504.5 pounds with one person, not person, it's probably, you know, some device that's holding this, whether or not it might be just some cables. One being supported, maybe this is a person at 120 pounds, and maybe this is something else attached to the ceiling, the loft. Anyway, 504.5 pounds is the weight of the engine. We'll stop there and then come back to a couple harder problems. Plus, I'm going to snag a vector problem that involves water current. And, well, actually, it might be a problem that involves wind speed. So I'm going to get a couple more problems where the angles are not perpendicular to one another.